Good morning, everybody. This is Hasan Aktarakçi, from European office, and thanks for joining our third short webinar. Uh, this week we will see about EarthImager 3D, and I hope everybody can hear me. If you have any difficulties hearing me, just you can send your questions or raise your hand. I will try to figure it out. And now again, I put one handout about this short presentation about EarthImager 3D. You can download it. And following this webinar, again, we will send you a link about the recording of this webinar, and you can also watch later on. If you have any question, you can just type it on this during the webinar. I will try to answer after this short presentation. If not, then you can send me email later on. I will try to respond all questions related. Thanks for joining again. This is our short webinar on EarthImager 3D. Again, I will go through this short presentation, and then following this presentation of the EarthImager 3D, I will go through the software, show you all these the features and how to read your data, how to process it, and how to get your result, different section, rendering, volume rendering, try to do also the real 3D and then parallel 2D lines, combination of the 3D. And I will do also some command file preparations and 3D command files, and then using that command file make some modeling, and I will end up this presentation like this. This is same like like what we saw last week in EarthImager 2D, which is what we call it 3 steps, and like read your data, change your setting, start inversion. So we create our softwares as make it easy to everybody can do this like 3 steps that change different setting. You will see that like last week EarthImager 2D we had many different settings as well. Here you can use like a surface setting, borehole settings, and conductive earth settings like this. It will help your adjusting your parameters of the forward model parameters, data removal parameters, inversion parameters, and easily. In this case, you can do it quickly and easily. Almost it works more than most of the data sets. If you have anything special, of course, you can just go through settings and you can change all these parameters like data removal parameters, mesh parameters, forward modeling parameters, and so far the others. Here is the showing, let's see, the EarthImager highlights. There's a function of mouse button. It's easy to use in rotating your image and zoom in, zoom out. You can have also the transparency control. We will see that static dynamic slices, 2D versus 3D, and volume estimation, 3D inversion with topography. Also, you can do that. And we will see like 3D survey planner. And if anything like monitors repeated data, you can also do for the time-lapse inversion on this one. Is typically in the 3D survey, what you do is you generally just go through like this is 3D layout. So start your electrodes from one corner, and then you can just go through. Let me just change this to like just go through like this, and then go back over here like this, or other way around because of cable here. So this is like a typically 3D layout, like a regular grid. You can do like a rectangular or square grid it's easy to do in the field. So that's what we call it is here, the rectangular grid ground surface here, like it's also showing here 1, 2, 3, 4, and 5 lines. Of 5 lines is a combination. You can also do these lines separately and then combine them, make a 3D. So we generally say this is the like a rectangular grid is almost a real 3D layout. And when you do like a parallel lines, let's assume these are parallel lines, and as long as this parallel line separation is maximum twice of electron separation, then that's also almost real 3D. Like sometimes they call it quasi 3D, but I will say exactly you will get the same results as long as line spacing twice of electron spacing. So that's the important part for to make this the parallel line combinations. Of course, you can do like a large separated parallel lines. Then you can do in the inversion as well, but that's not real 3D in that case, no, because of the very wide separated to the line spacing. Then you will be losing some information between the lines. In that case, it's kind of the and 3D comes interpolation between those colors and between two large separated lines. That's why, like, as long as you keep this line spacing maximum twice of electron spacing, then everything like a real 3D. So here is the line spacing. Let's say you have a electrode. Here's like a feet, like a line spacing is 100 feet. Electrode spacing, let's say here is like a 50 feet. That's what I'm saying. If you have a 50 feet electrode spacing, then line spacing should be maximum 100 feet. Of course, you can do also the 50 by 50, like whatever electrode spacing is. Let's just talk about this here's meter. Like if you have an electrode spacing 1 meter, you can put your next line over here also 1 meter or 2 meters. So again, if I just go to the just this one and then don't do the second one, do this one, don't do the third one, then you can just use these 3 lines, and then in that case you have a gap between the lines here because you will a little bit you don't have information on this measurement. So then still you can do 3D, but be careful about interpretation. So it will give you some information, but it will be a little bit, let's say, uh, um, uh, lack of information between the lines. So, but it still will be useful. And there are cases that people just do it like a large and let's say crossing line, and it's not recommended the crossing line, for example. As long as you keep this parallel line combination, the processing takes less time. Of course, if I do like one line here, one line like this, let me just clear up over here. Okay, like you have one line over here, okay, and then you do like another line over here, or another line like this, or like this. Okay, can I do like a 3D? Yes, you can do that, but this will take lots of processing time because of you're going through from regular grid to irregular grid in this case. So, and also be careful about this because you don't have many information over here. So you're just trying to make interpolation a little bit different colors at the end, because it's recommended to keep parallel lines, and then line spacing again recommended maximum twice of electron spacing. So if you can do this, you will really get a real 3D result in that case. So here is like 4 boreholes, 5 boreholes here. You can see here like boreholes, 1 borehole here, another 2, and then 3 and 4. There's another one middle, 5 boreholes. So I show this because you can really see volume rendering on EarthImager. So you can make like the slices, vertical slices, horizontal slices, like the vertical slices like this. You can do horizontal slices or cross slice between the diagonal directions. Or you can do like a volume rendering here, and you can just highlight whatever your interest. Here, maybe your interesting is in the low and high resistive anomalies. Then you can really see where those high and low resistive anomalies located. Sometimes you can just go through for let's say um, uh, get one interval, resistivity interval that corresponding your anomaly, and then you can just render that information, and it will give you that for a volume of this related resistivity information. So sometimes it can be used for ore estimation, for example, for mining, or you can do for excavation purposes. You try to find this to like there is an overburden material. Let's say you're looking for aggregate mining. Let's say you want to know how much material, overburden material, you want to remove, and you know that resistivity value, the material, you can just render that information with related resistivity value. You will see that how many meter cube volume material you will be estimated in the area. Okay, it's like a mouse button. It's make it easy to uh, rotate the image. You can rotate your image. You can just zoom in, zoom out. Like you're using here a left mouse button, you can rotate. Right mouse button, you can zoom out and or zoom in. Middle mouse button, you can you can just go through the zooming in, zooming out again in the images. It will really help, but I mean, you can play. If you have a EarthImager 3D, you can just play around. If you have any question related, and don't hesitate asking me. The other is like transparency control or rendering. So you just go on color scale, just on the color control properties scales there, or color scales. Just click there, you will see pop up this color control properties. And from there, you go opacity, and this opacity, you will see this the colors scale of resistivities, and you can just turn it off any color, turn it on any color over here. And if you just go through something like this, you can get like a transparency because you're just turning off almost high resistivities, giving more color option in the low resistivities. It will give this different kind of images. So you can play however you like to render this color rendering and volume rendering. Then you will help you this to interpretation, because at the end you're trying to find out where my anomaly located. So for presentation of your anomalies with this form, it will help you at the end the interpretation. So you know exactly where that, for example, you could for something maybe conductive zone in the here for mineralization maybe, no, then or some cavities, high resistivity values, then you can just highlight that part. You can see that location and volume, and not only for the depth, you see also extension. Remember in the first webinar 2 weeks ago, we started this with 1D. So 1D, what we were saying, nothing, just everything related with depth, nothing is changing. Neither X direction or Y direction, everything only one Z directions. Then next week we did like a 2D. In the 2D, we have seen this part or this part, let's say. What I'm trying to say is the resistivity only was changing depth and X direction. Now, in 3D, you have complete and you have all information changing with depth, X direction, and Y direction. That's exactly we try to find in the field, or we try to interpret looking through our 1D or 2D data generally. So like a 3D at the end, you will really see that the corresponding what you're looking for, and it will really help for interpretations. It's again the slices. There are two types of slices in EarthImager 3D. You can do what we call it is the static slices, like here, and dynamic slices. So you can get like X direction slices, Y direction slices, and depth slices. You can also get. You choose any of these intervals, and also uses a cross diagonal slices. You can also get it. In the dynamic slices, you just get 4, and then you just go to it. I will show you shortly this in EarthImager 3D. And you just move these slices, and also you can flip in right and left. You can locate exactly how or highlight your anomaly, and then just like here, and you can see white lines, which is when you push in left mouse button, it will just corresponding this point over here, and it will show you the resistivity coordinate of this point and resistivity of this value. So especially for when you highlight your anomaly, you want to give your drilling locations. So what you're looking for, you gotta drill, find out that will be your drilling coordinates over here, and then your resistivity corresponding that anomaly. Okay, the other thing is if you have a topography, and then you can also incorporate topography. So like last week, somebody asked is our software, does our software incorporate topography after inversion or before inversion? So like I know there are some software they do first in the regular grid in the flat surface inversion, and then shift everything and up and down based on the topography. So that's not like the way it's supposed to be done. All these processing, the processing has to be created first, the mesh with topography. So like if you in this case the software has to create 3D mesh uh, with topography, and then put all these in the mesh in values of the model parameters, and based on that, the mesh with topography, then do the processing, then do the inversion. That's EarthImager does. So what you do is read your data first, and then you need to read your terrain file before doing any inversion. So the typical terrain file is similar to like EarthImager 2D. You have here is the headers, and then what you need to put X direction, X coordinate, Y coordinate, and elevation. So all you need to do is you don't have to do every electrode X, Y, and Z coordinates. I mean, you can just, you get maybe one point over here, another point over here, okay? And then maybe just more point over here, and then you get another one. So maybe you get these points, let's say same thing is corresponding maybe here, like this. So that means that as long as you describe for your topography, it doesn't matter. So you don't have to get every points. So that for descriptions of the terrain parameters. So what I mean is get your terrain, X coordinate, Y coordinate, elevation. As long as this, you can create this and then just save it as a TRN file. And then you need to read this later on the process. For modeling, so to do modeling, again, we need to create one command file and then read that command file. When you read command file, it will generate a mesh with your whatever your geometry is, the electrode geometry. Based on the electrode geometry, create a mesh. And then this mesh, you can just put your model, like here we put it here like a conductive and resistive anomaly, and background is, for example, 100 ohm meters, and then just model it. You will try to see, for example, sometimes what you do before going to field, and you try to model your expected the lithology or whatever you're looking for, and then try to find out, okay, if I'm detect this anomaly in such condition, such geometry, such command file, different array types, and how the response will be. Then you can do this kind of the playing in the games. Okay, like we have this EarthImager 3D CL, what we call is command line. EarthImager 3D has a 30-bit platform. It works on all Windows 64, 64-bit versions, no problem. But when you have a large volume of this 3D data, it is hard to do this sometimes in EarthImager 3D 32-bit version. So in that case, you need to use is a EarthImager 3D command line version, which is a 64-bit platform. Then it doesn't have a graphic interface. It just run it at the platform and like a parallel processing, multiprocessor machines, like everybody now has in the multiprocessor almost in the small laptops, and you can just run it. Sometimes, let's say, if you do many lines, combine those many lines, and at the end you end up maybe 500 or 1,000 electrode locations, and maybe that 50,000, 100,000 data points, and then you can do that also in EarthImager 3D in Windows graphic interface, but it may take some time. Sometimes takes hours, sometimes takes more than a half day or 1 day. In that case, you need to maybe just run your software and overnight and see the next day. But sometimes it crashes because of the depending on your computer, memory is not sufficient to handle that kind of the data. So in such cases, you can use EarthImager 3D CL. Then it will work as just maybe you're just lowering your, let's say you do the 4 hours of the inversion, and you can do this less than an hour. Maybe then it will take half an hour or 1 hour maximum. All is depending on your computer speed and memory and all this CPU. We have also is a in computer like 8 cores and 80 gigabyte RAM processor in the main office. If some clients has a large volume of the data, we can do that for processing also with some cost. I just go to now to EarthImager 3D. Okay, here you can see is EarthImager 3D, and just let's go to and read. Okay, read the data. Okay, read the data. Here we have in the under demo directory, we have some data. We can read it. For example, here is like a, for example, let's just do a hill 3D. Okay, like the topography. Okay, when you read here, and here it will show your electrode layout geometry, and the right side is corresponding apparent resistivity. This is not like this 2D. Let's say in 2D, and you have a everything related with depth. Here is not easy to show, and only what we are showing here. Color scale of apparent resistivity is here, and then is X direction and Y direction related with the transmitter and receiver pair distances in each other. So sometimes it doesn't make sense, sometimes it makes sense when you get used to it, and you can see some highlighted colors over here which related to noisy data, and you can see it. Okay, here in this geometry, just go through after reading, read your terrain file. Okay, here we have terrain file. Okay, let me show you this terrain file. Okay, here the terrain file you can see is headers, and then X, Y, and Z. elevation, and x coordinate, z coordinate, and elevation. That's like a typical terrain file. Okay, just go back over EarthImager 3D again. Okay, just let's read this. Okay, we read that terrain, and then this is a surface, again, like a presetting. You can choose surface, cross borehole, or conductor first. So this is the surface data, just surface presetting. So that means that when you choose this presetting, you're just changing this, again, this data removal. These are exactly similar to EarthImager 2D. If you have already is seeing my video, recording last week or attending this seminar, we go through all these in features, and this is similar same thing. If you have a negative resistivity is not acceptable, you can remove. So it's remove automatically generate. You can keep all your data, or you can change your minimum maximum values. You just to go through like a surface setting. When you click surface setting, it comes like a inversion method is like a smooth model inversion. If you have a loss of the let's say irregular grid, you can just put this special borehole data, or sometimes the large parallel lines, you can just snipping electrode distances. You can put like a 10% of electrode distances. If you have a 1 meter, you can just put like a 1. That will be speed up your the inversion process generally. Okay, and here's the typical presetting comes finite difference. You can also choose finite element, takes longer time. Sorry, it's also, you can change your the mesh division. Default comes in the 2 mesh division between the, two meshes, 2 cells between electrodes. That's like a typically in maximum survey resolution. And inversion settings, you can also like a stopping criteria of inversion, smoothness factor. If you have a noisy data, you can increment this maybe 100 and more. It will also change sometimes damping factor. It's same related with the smoothing, more or less the 100. If you have IP data and also do linear IP inversion after finishing rested, just do one linear IP inversion in our software. Okay, just go on the surface, and we already read the data. We did this, and then just inversion. Okay, here like you can see this, and I can with left mouse button, I can try to rotate my image. You can see that it already created this topography mesh. Now trying to generate this to inversion. So like here it will take some time. So that means maybe it's a couple minutes of doing it. Okay. So if you have a large volume of data, it will take maybe hours. In that case, you can see that if you have already EarthImager 3D, but if you don't have a EarthImager 3D CL module, you can purchase that separately. When you purchase, we send this activation code on your dongle, and then when you're activated, you will see over here like what you can see, and let me highlight that. You can see here this 64-bit. Maybe some of your of you have EarthImager 3D doesn't have this because you don't have that module. When you purchase separate that module, you will have it. Once you have this, you can just also run this through an EarthImager 3D. So it's almost done over here. Is in the third iteration now. So RMS is going down to 20. So like the image almost is getting ready. So we can also just stop over here, but just let's wait. Again, it's you can just click on here 64-bit. Let's just wait to finish up this inversion. I don't want to be mixing up all this here. And then we can just see this result. Okay, here and now is iteration number 6. It's almost getting done. Okay, 6 and 7 will coming. So each time when the iteration continue, you can see that RMS is going down. Again, like what I said in my earlier presentations, in RMS is less than 10%, it will be acceptable. It doesn't has to go to like a very low. Some people really focus on is if RMS is like a 1-2%, I get perfect. No, as long as I recommend as long as you go to RMS is less than 10%, you're in a good shape. Sometimes you have a noisy data, sometimes other things, still RMS is the high and it's representable. But in a good data set is an FEV iteration, RMS, it goes down less than 10%. Here we have some little bit highlighted outliers, and we can just reduce it, remove it, and then do inversion again, reduce RMS maybe less than 10%. And let me show you one thing over here. If you have this an inversion setting, okay, if you have a noisy data, if you click over here, and then you can see L2 norm click automatically, okay? Do you see that? Okay, in that case, what happens if I do this data with L2 norm click and suppress noise data? So that means if I have a noise data, I use this suppress noise data. That means I give less weight my noisy data parts and then more value, more weight to good data side. So that statistically I can do that in that case, and I don't care about RMS. I have to focus on L2 for which is L2 is normalized RMS generally. So it will be about 1. So not too low the 1, not too high the 1. So it's about the 1, around the 1. Okay. So unclick this and then just go through like here. Okay. What is the next step over here? After finish this, RMS is 13. I just go to here, histogram under view. Histogram is with histogram, and then just go on the keypad and the left and right mouse button, and then just go through all the way. For example, and here I have like a here right side you cannot see color, but it shows here 2 data points. So you can remove like a little bit data here. For example, maybe it's like 12 data points of let's say more than 70% misfit of the 12 data points. You can remove, you can redo this inversion and it will lower than RMS less than 10%. Okay, we don't have to do now. Is just go through this the presentation on this. So just go to the inverted under view, inverted resistivity model. You can see your resistivity model. Okay, again here is in the mouse reel, middle reel, and then you just go zoom on, zoom in, zoom out. On just go to same thing as a right mouse button. You can do that, and then left mouse button. You can turn your the images. You can really see how your the anomaly related to other side. So you can really zoom in, zoom out, and then turn and try to understand just what corresponding that structure. Okay, here is the what you can do. So you can get the static slices. Okay, again like in the static slices and X direction, Y direction, and Z direction. So depending on how many slices you like to do it, for example, you can do it. Okay, you can just do like this, and you can get multiple slices like this. Okay. And other thing is you can just get also the contour. Here you can see that dynamic slices highlighted. That means you cannot do, when you have a topography, and then you cannot do dynamic slices. If you have a flat surface 3D volume image, then you can do the dynamic slice. I will show you with another one, that one. So the next one is the 3D contour models. I mean here you can choose how many intervals you would like to do it. Okay, like here, apply, And then you can also turn off some colors or whatever you like to focus on. For example, you can do that, or you can just choose apply and different intervals. So you do anything is the convenient for you to try to understand or try to show exactly where the anomaly is located. Okay, if I do, for example, interesting in the high resistivity zones, I am just turning on, maybe turning off of all these low resistivity, turning on the high resistivities. Okay, and I see like this way is the 3D images. Okay, just go through here is the inverted resistivity model. What you have is also here easy color contour windows and also volume rendering method. Here you can see volume rendering method, race skating a map surface in the terrain is not available again, but for example, texture is not available in the when you have a topography, and you can also just go to the, like this in this case to uh, uh, rendering. Other thing is just go to color windows, and then you can change your levels. Okay, you can use different up to 156, for example, or 32, 16, any color interval you like to do, you can do that. You can choose minimum and maximum. For example, I will choose maybe 1 to 1000, and I apply this. I can really see different color images, and it will all try to make it different way to understand what structure corresponding there under the ground, and then I can go through the make it easy for me to interpretations. Then the other things was the opacity. Okay, and then we just go to opacity, and opacity here. When you go to opacity, it will come this color opacity pop-up window. Now here you can also turn off any colors. Let's say like here, and then just go through. Okay, and then now you have this high resistive anomaly. It shows you also here total volume of this image, which is meter cube, and opaque surface, which is about 693 meter cube. So like if you like to make estimation of this anomaly, whatever corresponding your expectation, can be uh, structure or anything, and you know that what volume of material you have there to especially for mining investigation. It's very easy useful tool to get ore estimation, for example. Other opacity parameter, for example, what I said, you can do like a transparency, less colors over here and more colors and a high resistivity again, and then it doesn't show too much, but you can just go to maybe more like this. It will show you a little bit more. Okay, like this. Okay, I will read another data which without topography. Let's say just go maybe borehole data. Again, now here, what this is the boreholes, like a 5 boreholes. Then I will choose cross borehole presetting. Okay, I will choose cross borehole presetting. Let me just show you here. Okay, when I choose like a surface presetting, okay, you can see also the here parameters. There are some parameters it's automatically check over here spreads noisy data. It's typically normal having a noisy data and the boreholes because sometimes when one electrode is too far away from other borehole or the diagonal distance too far away, weak signal, and it will create noisy data. So typically in this case, you can just start with this noisy data, spreads noisy data option. In that case, it will be focused on only L2 norm. So what was L2 norm was about the normalized RMS, which will be about 1. Okay, just go to the inversion. Okay, it's going fast, and then it just show up here the image. Here you can see high resistivities in low resistivity zones. Here now L2 is about 1.2, so it's iteration number 5, RMS 19. So that means it's like a maybe we go like a earlier one. I mean, sorry, here like a 1.2 is okay, reasonable. Iteration number 4 or number 5. So like a number 4 is okay or number 5 is okay. So it's about 1. So the RMS is, I don't care whatever it is, but it's important to have here L2 is about 1. Okay, this is close to 1, and that will be okay in that case. Okay, so now I will go again. Here is the underview inverted resistivity model, and then you can just see this rotating and try to understand how your anomaly are located. You can go here in the volume rendering. Now I can choose this whatever, let's say I want to see this anomaly. Let's say isosurface 13.40 meters, so that's my target, for example, and I just go on OK, and I can only see this isosurface and relate it with this anomaly. So whatever your concentration of the anomaly, let's say the value of that anomaly, and you can just pick up that color and just present that information, and you know how that the distribution of that anomaly in the area. Okay, you can do that, or like this, or you can just go on texture mapping, and it will looks like a you have a multiple slice. It will show you a little bit different presentation, and you just go also the opaque surface like this, and then you can just go. You also change your color scale, like for example 256 color, and you can change also the interval, whatever. Okay, and it will be for different presentation purposes. You can also get here opacity, and now I am really interested to with here low resistive and high resistive anomalies. What I will do, I will turn. So if I pick up this like a 250 colors, you can see lots of the lines over here. So that means I am like trying to go a little bit turn off all these. So now I turn off this and turn off this and try to get this high resistive anomalies more than 30 ohm meter, sorry, and then it's about 2.5 ohm meter less anomalies. I tried to highlight it, and then now it shows me this. Uh, so when you turn, an image gets fuzzy, and then when you just leave it like this, it will show you exactly after rendering is finishing. So rendering takes a little bit time, but it will show you this location of this high resistive and low resistive anomalies. So this is like a typical 4 borehole, 5 borehole contamination purposes study. It has been done a long time ago, and it will show you this contaminated site, like high resistive and low resistive zones in the area. Okay, this is a, I think we can go to the more, and but it will you can just go to and here is if you have a EarthImager 3D, you can just click that EarthImager 3D CL 64-bit version, and it will be here in the data, and then it will just go to the start processing. Do you see like processing is what we did on other. Now it took about 5.2 seconds of runtime of this. So RM is about 13 and L2 is about 0.76. So this is like a large volume of the data. You can do this EarthImager 3D CL and then just running like this here. So once you're done, and you need to just uh, go back and then read your inversion output. So that inversion output stored in different director, like a processing director here. So that means that you can just go and read that output. Okay, so it will be your output here, for example. I think we read this in other one. Okay, I think all about this the quick features, but let's just go through now is the how to create some command file, and that makes modeling simply. Okay, just go on under tools, 3D command creator. Okay, here 3D command creator is which is regular, rectangular, or square grid. We can do that. If you have an irregular like a square or triangle or surrounding a building, in a special case, electric configuration geometry, then you need to create first here regular, rectangular or square, and then you can modify by hand later on. So depending on how many electrode you're going to use, for example, 56 electrode. So how many electrode I'm going to put X direction, for example, 8. How many electrode I will put? 7. So 7 times 8, 56. So what is my electrode spacing X direction? Let's say 1 meter. What is in Y direction? I will put maybe 1 meter also. So just set up like a geometry. Okay, just set up like geometry like this, and then okay, if you want to change orientation, change X direction like cable orientation. Okay, like this. Once this is your field setup. So like everything starting is 0.01, first electrode, go to like this, like go 7, 8 electrode, turn, and then like this. Okay, this is a 1 by 1 meters, a regular grid, 56 electrode. So you can do whatever is your study area. In this case is like a square, square, and rectangle, rectangular. So once you wanna modify, here is all your geometry. So that means what is your first electrode, coordinate, X coordinate, Y coordinate, Z coordinate. Now you can change all these 5, for example, and you can change all these, whatever is modification. You can modify your electrode geometry. Then you can just save this geometry, okay? And then it will save it, and then you read again that geometry, okay? Then you can create special cases of your of your, let's say, uh, surface layout. Okay, I'm just going to, this is we don't change over here, everything is same. Okay, Jan, what is next? And we create this geometry first. After creating geometry, you need to choose which array type you would like to, let's say here what we have, pole, dipole, dipole, bipole, gradient, radial, gradient, and radial dipole. So typically is mostly used in dipole, and radial dipole is in 3D, and also pole is mostly used in 3D. Why? Because if you do like this uh, almost square layout, let's say I have a 7 meters here, 8 meters, 6 meters other side. So if I do like a pole, I can really get about 6 meters depth on this one. So like one side of the like a square, and it's your investigation depth when you use a pole array like here. Okay, and then just create it, and then you can see over here simulations. Um, it's the estimated depth about 5.5 and 6 meters. Okay, and then once you create it and save this command file, and this will be saved here under EarthImager 3D. Okay, save. Okay, let's just save it. Okay, I will just save it over here. Just save it. Once you save, and then just go on File, and then under the file, read your comment file. Okay, read your comment file. Okay, here is the, I think, where is that EarthImager 3D, and under demo directory we have a temporary, and here there are other comment files, but what we create just this one, temporary. Open that one. Okay, once you open it, you will have this mesh over here. Let me just go through, and here left side, and I have you have two color scales. I mean, here's 10 and 1000, blue and red, and also background 100 ohm meters. So if I want to put a mesh, like this is the mesh, is typically what you have a mesh is based on your forward modeling setting. It's like a two divisions between electrodes, so two cells between electrodes. That's for maximum resolution. And other things is here now, like you can just go through as let's say add resistivity. If you like to put different resistivity values here, you can just type any resistivity values, for example 25, add it. Okay, and then if you want to choose as, let's say, to the volume, like trying to add over here is like this is showing the block dimensions. So this is like you start to put blocks. Okay, just when you put like a block, add it. This is like a choose 10 ohm meters, blue resistivity values here. Now I am trying to put maybe I want to put this as a layer. What I can do, I can just put this in the corner. Okay, put the corner and the first corner over here, and then I try to put this now as extending an X direction and then Y direction, for example. If you want a thicker, you can do like this. So now I can create like a layer. So now depending on where do you want to put this layer, you can move this like up and down. Like this is the one. So background is 100 ohm meters. I put like a one layer of 10 ohm meters. So once you can create like in this way is your model. Once you create it, and just go to under tools, and here you can do survey planner. You do just one forward simulation to create the apparent resistivity data, or just a survey planner, which will create your apparent resistivity data, and then try to invert that to like here is what you see in the right side is apparent resistivity calculated based on this model. And now using this apparent resistivity, try to make inversion and try to see that if we can detect that information what we have already put over here. Or here what you see is more or less is 100, like red colors is about 100 ohm meter. Let's just put this like between what the value we put. Let's say 10 to 100. Okay. Okay, now what I put is 10 ohm meters, and it's up here a little bit, this maybe 30 ohm meters is layer over here. Why is that? Because it's always like a dominated factor. What is dominated factor is the more volume is the 100 ohm meters. So like we put on structure 10 ohm meters, but and you're expecting this as a appear is 30 ohm meters. So but reality, you know that this is 10 ohm meters, because of the dominant factor is the 100 ohm meters, get average of this to a little bit higher. Okay, one question comes like how you get rid of critical data. Yeah, sure. That what you do like here, what we did is inversion. Okay, and after inversion, you can, well, first of all, you can just go through. Let's just read the data first. Okay, just read this, for example, as again borehole data. What we did. Okay. You can just go to data under edit, data editing statistics. You can check over here. You have like it shows that depending on the setting, there are 52 data minimum voltage. Okay, so that's like it will remove about this 11% of 52 data is based on your setting. Okay, if I just go through like a surface and then read this data again, okay, and then I'll check this statistics. So now what I have is here suddenly, and now is 106 data points will be removed. So that's like a critical data, what asking and get rid of the critical data. This is your, based on the presetting, your critical data. But since this is a borehole data, don't choose this surface. Then you will remove lots of data. So in that case, you don't want to do it because what you have is total 45 electrodes, and in the left side, you can see 439 data points. So then you just go on presetting, cross borehole, read your data again, and then open, and then you can choose this data, and it will show you only 52 minimum voltage valve will be removed when I do inversion. So this is one way of to do this based on the presetting. You can remove that. If you want to remove some electrode, okay, you think that my electrode number 2 gives lots of problem during the measurement, I can remove that. So then that will remove related all critical data, noisy data with related electrode number 2. So you can remove that also like this. The other thing is, after finish your inversion, okay, let's just go through like here. I think after inversion, what I showed you earlier, just go to the misfit histogram and then try to remove statistically like noisy data. So that's your question, like get rid of critical data. So you remove like this little by in such way to until you reach your RMS or L2 values, reasonable expected, and then that will be your the way of the removing correctly your noisy data. So the first, when you did is inversion, don't remove nothing. Always try to choose, don't remove nothing. Sometimes if you have a noisy data, if you do that presetting, sometimes you lose many data. Don't do that. So if you think that you're removing lots of data, here I have 439, maybe I'm removing 300, no, that's not good. So then in that case, I can just go setting, okay, keep all data, keep all, and then you read your data, do inversion, and statistically in histogram remove little by little, and then do inversion again, go back histogram, remove little more, try to reach reasonable results. That's all my recommendation. Okay, I think is all what I can show you this week. Let me know if you have any other questions. If not, and then you can also reach me with the email. You can send me your email about your questions. Okay. If you wanna speak up, and you can also go to raise your hand, you can speak up. Okay, so far I don't see any more question, and I think which is okay. And thanks for all joining our this EarthImager walkthrough short presentation. Um, don't hesitate to contact me related to any question, and we can try to help you anytime. Thanks again. Have a nice day all. Bye-bye.